In this Tiny Methods workshop, we're going to be talking about descriptive statistics. So descriptive statistics describe and summarize basic aspects of our data. They allow us to simplify a large amount of information about our sample or our variables in a more easily understandable way. So imagine trying to make sense of, say, 10,000 measurements of height in a particular sample simply by looking at them. That's a lot of information to process just by a glance. But if we simplify this down into, say, the minimum height, the maximum height, and maybe the mean, we get a better handle on our data. And as the name implies, descriptive statistics are simply descriptive. They describe the data at hand, but they do not go beyond that and involve generalizing beyond what we have right in front of us, which is in contrast to inferential statistics. And this process of description and summarization does involve some trade-offs, including the loss of nuance or detail. So for thinking about an example like GPA, which is an average, is a grade point average, so mean, as a one-number summary of performance across a wide range of courses, we do lose some facets of that, such as the rigor of the courses that were taken. Okay, so now that we have a handle on what descriptive statistics are or allow us to do, we'll take a look at some actual descriptive analysis, starting with univariate descriptive analysis, which univariate, there's a union there, means one variable, so an examination of each variable individually. And there are three common considerations that we want to take into account for each of the variables we're looking at. So the distribution, which shows the frequency of observed values for a variable, and some common ways to look at the distribution include frequency tables, histograms, bar charts. Then next we have central tendency, which identifies the center of a variable's distribution, and mean, median, and mode are three common approaches to capturing central tendency. Then we have dispersion, which reflects the spread of or variability in a variable's observed values. And three common ways to look at dispersion are range, standard deviation, and variance, and we'll take a look at all of these more closely in the following slides. So starting with the distribution, here we're looking at the frequency of particular values for a variable, and this can be summarized in a table and or presented in a graph. So first we'll take a look at frequency tables. So for a categorical variable, which often has relatively few categories, a table that shows each category and its corresponding observed frequency and or the corresponding percentage to that frequency is simple, and it can be a sufficient way to present this information. For continuous variables, however, we often have a large number of possible values and potentially few observations at each of these values. So grouping them into ranges of values may be more efficient and meaningful in terms of summarization. So there's an example on the bottom right of this slide where we started off with a table of age in years with the corresponding frequency. The little dots in between indicate that this age range actually goes from 18, 19, 20 by years all the way through 25, just skipping over to 89 down. And we have the corresponding frequency to the right of that. But that's a lot of rows. If we would actually expanded that, I'd collapsed it. But if it's expanded with 18 to 97 by ones, that's a lot of information. So if we condense that down into some age ranges, so 18 to 22, 23 to 27, 28 to 32, 33 to 37, etc., all the way down to 93 to 97. And then we also sum up the frequencies in those ranges. We have a nicer, more condensed way of summarizing the observed ages in our sample in this case. Okay, so we've seen how we can take a look at the distribution in a table. We can also create graphs to allow us to visualize our distribution. So bar charts and histograms are good options for categorical and continuous variables respectively. And they do allow us to see the relative frequency of observations within a particular category for a categorical variable, or within a specific range of values for a continuous variable. And we will see examples of both of these types of graphs in some later slides. Some additional facets of the distribution of continuous variables that we might want to take a look at and that can be quantitatively summarized are skewness and kurtosis. So skewness is a measure of asymmetry in the distribution of our variable. So skewness will be 0 for perfectly symmetric data. So an example of this is the normal distribution. If you've seen that, it's perfectly symmetrical. Negative skewness indicates negative or left skew. In this case, we have a long tail drawn out on the left of our distribution, We will again see some of this in the histograms to follow. And positive skewness is positive or right skew, and in this case the long tail is on the right of our distribution towards higher values. Kurtosis is a measure of the lightness or the heaviness of the tails of a distribution, and this is relative to a normal distribution. So kurtosis would be 0 for a normal distribution. If kurtosis is negative, it indicates that we have a light tail distribution, and light tails tell us that there are fewer values in the extremes or tails of the distribution than a normal distribution would predict. In contrast, positive kurtosis indicates a heavy tail distribution, and with those heavy tails, we have more values in the extremes or tails of the distribution than a normal distribution. And sometimes these values that are toward the extremes can be considered outliers, which we will talk about further. And as a note here, in SPSS and some functions in R, this is the definition of kurtosis that's used, but double check that this is the definition in other software that you may use as well. So for example, while here kurtosis of 0 is for a normal distribution, in other definitions of kurtosis, the value for a normal distribution is not actually 0, it's another value. So just be sure that whatever software you're using is using the definition of kurtosis as you expect, and that's sound advice generally. Make sure that the software is doing what you think it's doing. All right, now moving to some examples. So here we have a variable, interest in internet, computers, and technology. On the right-hand side, we can see a histogram for this continuous variable. Then on the left, we have skewness and kurtosis. So skewness here is 0.28, so that's pretty small. It is positive, so we have a slightly positively skewed distribution here. We can sort of see that in our histogram. If we look towards the right-hand side of the histogram, we can see a sort of drawn-out tail towards the right. Not a lot, but a little bit. Then if we look at kurtosis, it's negative 0.28. So being negative here, this indicates that we have slightly lighter tails than a normal distribution. Okay, and another example. So this variable is the use of internet, computers, and technology for leisure. Again, we have the histogram for this continuous variable on the right, skewness and kurtosis on the left. Skewness here is 1.15, so this is a positive value. It's not massive, but it's fairly large. So we do have a notably positively skewed distribution here, and we can see that if we look at the histogram, we do have a drawn out right tail. And kurtosis is 3.99, which is quite a bit higher than the 0 we would expect for a normal distribution. So we do have markedly heavier tails than a normal distribution. And both the skewness and kurtosis values here seem to be pointing us towards that little blip on the histogram that we can see at around 3. It looks like we have an outlier or a few outliers up towards the high end of our scale. So this is pulling the distribution with that long right tail upward. And then like we mentioned with that positive kurtosis value, we do have heavier tails or sort of an outlier prone distribution, if we want to think about it that way, where we have some observations in the extremes. Okay, so now let's move away from the continuous variables and take a look at an example of a categorical variable. So here we have favorite color, and we have the frequency table with the favorite colors on the first column, then the observed frequency in the middle, and then on the right, the proportion, and you can easily convert that to percentage. And from here, we can pretty quickly see that blue is the favorite color. But if we want to look at this visually, we can take a look at a bar chart. So here we have the bar chart for favorite colors, but let's actually make this a little bit more fun. There we go. So now we can see for sure that blue is the most observed favorite color amongst this sample of 500, followed by a tie between green and purple, and then for the least favorite colors, we have a tie between gray and white. Okay, so now that we've taken a look at the distribution of a few different variables, let's talk about central tendency, which are estimates of the center of a distribution of values. So 3 common measures of central tendency are the mean, so the average value, the median, which is the middle value in a set of values, and then the mode, which is the most frequently occurring value. So let's go back to our examples and look at these measures of central tendency. So returning to the first variable of interest in internet, computers, and technology, I've added in the mean, median, and mode here. We can see that they're all around 0. They're pretty small numbers. The mean or the average value is 0.093, the median or the middle value is negative 0.00585, and the mode or the most frequently occurring value is negative 0.0862, and there are 50 observations of this mode. And as a brief note here, for a perfectly normal distribution, the mean, the median, and the mode would all be the same value. And we'll talk about this a bit further in a little bit, but when there are outliers present or the distribution is markedly skewed, the median can be a better measure of central tendency because it's not as affected by those outliers in skewness as the mean is. Okay, so for example 2, the variable is use of internet, computers, and technology for leisure. So again, I've added in the mean, median, and modes here in this case. So the mean is negative 0.024, so that's the average value. The median is negative 0.0864, that's the middle value. And then the modes, which we have 4 in this case, are negative 0.4309, negative 0.1811, 0.0413, and 0.8779. And there are 2 observations at each of those 4 values. And returning to what we had just been talking about with the mean being affected by extreme or outlying values, if we would take out those few cases that we've seen on our histogram as quite a bit up there, near 3 compared to the rest of the distribution, the mean would change to negative 0.043, so somewhat lower. So we can see here then that those 3 high outlying cases are pulling the mean toward them. And then for our categorical variable example here, for favorite color, the only measure of central tendency that's really meaningful for this categorical variable is the mode, which is blue. We've seen that before. Blue is the most frequently occurring category for this variable. So now we've talked about the distribution, we've talked about central tendency, and finally we have dispersion. So dispersion is an indication of how spread out the values are. And there are 3 common measures of dispersion that we'll talk about here. The range, which is the difference between the maximum value and the minimum value. Then we have the standard deviation, which is a measure of variation, and it's the squared root of the summed squared deviations from the mean divided by the number of values minus 1. So if you got lost in all those words, the formula for it is directly below there. And a standard deviation is interesting and useful in that if a variable is normally distributed, approximately 68% of the values will fall within 1 standard deviation of the mean, 95% will fall within 2 standard deviations of the mean, and then 99%, so most of the cases, will fall within 3 standard deviations of the mean. So the mean and the standard deviation often go hand in hand, including in reporting, which we will talk about as well. And then the variance is also a measure of variation, and it's the squared standard deviation. So if you take off that little square root of the formula of the standard deviation, you're left with the variance. So some examples of dispersion here are our 2 variables that we've seen before, our continuous variables. On the left, we have our interest in internet, computers, and technology variable. The range, the highest value is 1.7671. We subtract the lowest value, which is negative 1.4316, and this gives us a range overall of 3.1987. The standard deviation is 0.646, and the variance is the square of that, so 0.417. Then for our use of internet, computers, and technology for leisure variable on the right, the range is the highest value, so 3.1399, minus the lowest value, which is negative 1.5043, which gives us a range then of 4.6442. The standard deviation is 0.576, and the variance is again the square of that, 0.331. And both of these variables happen to be measured on the same scale. It's the latent trait scale from IRT, or item response theory analysis. So if we look at the range, we can see that the use of ICT for leisure variable has a somewhat wider range than does the interest variable, while the interest variable actually shows a bit more variability or variance than does the use of ICT for leisure variable. Another helpful consideration in univariate descriptive analysis are box plots. So they allow us to visualize a variable's distribution, similar to a histogram, but from a different perspective, capture central tendency in the form of the median, and show dispersion as well. And the horizontal lines forming the box of a box plot, which we will see in a moment, are at the first quartile, the second quartile, and the third quartile. The first quartile is the value at which approximately 25% or a quarter of the observations fall at or below. The second quartile is the value at which approximately 50% or 2/4 or 1/2 of the observations fall at or below. And that matches the definition that we saw earlier for the median. So the second quartile and the median are the same value. And the third quartile is the value at which approximately 75% or 3/4 of the observations fall at or below. Then the vertical lines extending from the box reach to the furthest values that are less than or equal to 1.5 times the interquartile range. The interquartile range is calculated as the third quartile value minus the first quartile value. And then any values that fall beyond those lines can be considered as outliers. So from this definition of an outlier then, an outlier is any value that falls outside of 1.5 times the IQR or interquartile range for the particular variable under consideration. Okay, for an example here then, we have our interest in internet, computers, and technology variable. And again, the box part of our box plot, the bottom horizontal line, is the first quartile. The bolder line above it, near around 0.1, is the median or the second quartile. And then the line above that at around 0.5 is the third quartile. And then extending from the box, we have the vertical lines that are reaching to the furthest observed value that is no more than 1.5 times the interquartile range. And looking at the box plot here, we can see that it's fairly symmetrical, which also corresponds to the small skewness value that we saw towards the beginning. And then continuing to our second example of the use of ICT for leisure variable, we can see that this box plot looks definitely different from the one we just saw. So we can see the main body of the box plot again, the bottom line, the top line indicating the first and third quartiles, with the bolder line indicating the median, the extended vertical lines reaching to the furthest observed points that are no more than 1.5 times interquartile range. But then we also have a bunch of dots below and above those vertical lines. And these then are the observed values that are greater than 1.5 times the interquartile range. And I did call out on the right-hand side what the actual observed values are for those points. So we can see our maximum value, 3.1399, hanging out way above our box. And then we have two negative values also hanging out below. So in this case, we have two low-lying negative outliers and a handful of positive high-lying outliers. Speaking of outliers, as we've seen, these outliers do stand out from the other observations. They outlie the main body of data points. There are different types of outliers, so what we've seen so far are univariate outliers, which differ markedly from other observations on one variable, but there are also multivariate outliers, which show a combination of unusual values on two, which is bivariate, or more variables. And outliers can, amongst other things, strongly influence the range, be either inflating the maximum, decreasing the minimum, or the mean, and they can be problematic in further analysis. There are further analysis that you might be interested in that assume a roughly normal distribution with no marked outliers. So if you do have outliers, it's something to think about. And they can occur by chance, but it's important to also carefully consider why a particular observation may be identified as an outlier. So for example, has there been a mistake in data entry? Did you mean to enter 40 and accidentally entered 400? Is that odd 99 hanging out way apart from the rest of your observations a valid value? Or is it actually a missing data code that just simply hasn't been treated properly as a missing data code? So as just mentioned, be sure to know how missing data are coded in your data set. So 99 is clearly not a valid value for age in years if data are collected only from adolescence. So you would set that 99 then to missing and you're okay to proceed. But other missing data codes may not be so obvious. And this is particularly important if you're working with data that you are not personally involved in the collection of. So be sure to understand how missing data are treated in the data set that you're working with. It's also important to be aware of how missing values are coded in the software you're using. So missing values in R, for example, are represented by NAs. So if you're expecting missing data on a particular variable, you should have NAs there. That's a very quick check that things are coded as you would expect. And once missing data have been properly coded as missing, a quick check then of the number of observations for each variable, or more directly, the frequency of missing values themselves, can indicate the extent of missingness. So continuing with our 2 example variables we've been working with, here they have been coded as NAs, and we can see from this little summary that we have 2 missing observations for the interest variable, and we have 4 missing observations for the use for leisure variable. Then after you've identified the presence of missing data comes the often weighty, complex, sometimes controversial decision of how to go about handling this missingness in further analysis. But once you know you have missing data, it's important to think about what you're going to do with it as you proceed. Okay, so let's put this all together then. Here's a new variable. It's perceived autonomy in ICT, Internet, Computers, and Technology. So what do you notice from what's presented here? We have the mean, we have the median, we have the mode, we also have the range, standard deviation, variance, skewness, and kurtosis, and then we have a histogram and a box plot. Is there anything else that you would want to know or look at? So feel free to pause this video and to think about how you would describe this variable, and then I'll point out a few things that I noticed or that I might want to know in addition to what's presented here. Okay, so from the mean, we can see that the average value here is negative 0.1554, the median, the middle value is negative 0.1563, and the mode is 0.1216. Then we have the range, 3.7335. Here we might want to know the minimum and maximum, and do they make sense for how we know this variable is measured. We have the standard deviation and the variance there as well. And then we have skewness, which is positive, fairly small. So we see we have some slight positive skew, which we can also see in the histogram. We have a little bit of a tail drawn out on the right-hand side. And kurtosis is 0.22, so we have slightly heavier tails than a normal distribution. Then looking over at the histogram itself, again, we noted some slight positive or right skew here. If we look at the main title, we see that the N is 496, so the valid number of observations on this variable is 496. So something that you might want to know in terms of missing data here are how many observations were there in total, what was the overall sample size. In this case, it was actually 500, so as long as missing data were coded properly, we have 4 missing observations for this variable. And then looking at the box plot, we can see that we have 6 high-lying outliers, which also sort of matches with what we've seen with the slight positive skew, and then we have 1 low-lying outlier. And the bold horizontal line in the box is right below 0, which is the median, and if we look over at the actual value of the median, it's negative 0.16 approximately, so these match like we would expect. And then a note on reporting here. So which aspects to report from descriptive analysis and how you go about reporting them depends on, amongst other things, the type and purpose of your research, the venue. So is this a manuscript you're submitting to a journal where you're going to be within certain constraints in terms of length, or is this your dissertation where you're going to need to be as thorough as you can be on what you've done? And also your anticipated audience. So are your readers likely to be familiar with terms like skewness and kurtosis, or are you going to need to be a little bit more thorough in how you go about discussing these ideas? And in general, in-text reporting may be sufficient when you have a small number of variables that are under consideration, while descriptive information about a large number of variables can often be presented well in a table. And as an example of a table here, this is just a little one looking at the variables that we've seen so far, and this is in APA style. So we have the variables running along the left-hand side, then we have the valid sample size, which indicates missing data if elsewhere you've indicated that the overall sample was 500. Then we have the mean and standard deviation, the minimum and maximum, and the skewness and kurtosis. And then there is a note at the bottom indicating that this abbreviation, ICT, stands for Internet, Computers, and Technology. And again, this is just one example of a table what you may choose to report can be different, again, depending on the type of research you're doing, what you're looking at particularly, where this is going, who you're talking to, that sort of thing. So up to this point, we've looked at univariate descriptive analysis, so one variable at a time. We can also look at bivariate descriptive analysis, and like the name suggests, here we have two variables. So we're looking at the pairs of variables in this case. And we can describe some basic features of the relationships between them by looking at scatter plots, which allow us to visually consider the direction and strength of the relationship between our two variables, where correlations provide a numeric summary of this relationship. So an example scatter plot here, this is between the variables we've seen before, the interest in ICT and the use for leisure. We can also see in the main title there that the valid sample size for this particular consideration is 495. So amongst our 500 overall observations, only 495 of them had a valid observation on both the interest and the use for leisure variables. And those are the observations that make up the scatter plot below. So looking at the scatter plot, we might notice a couple of things. So we do have a few points along the use of ICT for leisure axis, so the y-axis, that are hanging out near that 3, which we've also seen before. We did have some univariate outliers there. We can see them also separated from the main body of the scatter plot. Then looking at that main body, we see not a particularly strong relationship, but there does seem to be some relationship happening here. We can sort of see an upward slope as we move from left to right. There seems to be a bit of a positive relationship here. So that in general, there seems to be a tendency that as interest in ICT increases, so does the use of ICT for leisure, which seems to make sense. And if we add in the regression line here, we can see that there is indeed a positive upward slope. Okay, so we can also summarize what we've just seen in the scatter plot using, again, a numeric summary in the form of a correlation coefficient. So a common type is Pearson's product moment correlation coefficient, which measures the strength and direction of the linear relationship between two variables. So this coefficient ranges from -1 when we have a perfect negative relationship to +1 when we have a perfect positive relationship. Pearson's does assume that both variables are continuous, so they're measured on either an interval or a ratio scale. And this type of correlation coefficient can be markedly influenced by outliers and non-normality. So if we're looking at the associated tests of the null hypothesis of no correlation in the population, which is rho equals 0 if we're looking at the null hypothesis at the end there, which that might look like a p, but it is a Greek rho, then we do need to check that normality holds or is at least tenable amongst the variables that we are considering. Then other options are available if your data are, for example, measured on an ordinal rather than an interval or ratio scale, or if that assumption of normality is not tenable. So for example, we have Spearman's rank order correlation. So Spearman's is non-parametric and it does allow for ordinal alongside interval or ratio data, but rather than measuring the strength and direction of the linear relationship between two variables, it instead measures the monotonic relationship between these two variables. And a monotonic relationship is one in which, as the values of one variable increase, so do the values on the other variable, or as the values on one variable increase, those on the other decrease, but not necessarily in a linear fashion. So as an example of correlation, we've seen the scatter plot already, and capturing that positive, not too strong, but somewhat of a relationship that we've seen there. The Pearson correlation between these two variables is 0.273. So it is positive, and it is there, but it's not particularly high. Then if we want to summarize these correlations for all of the continuous variables under consideration, we have a correlation matrix. So this one here shows 7 continuous variables. And something that you might notice in the blue R code right above it is we're using pairwise complete observations here. And this means that the correlation for each pair of variables is based on the number of valid cases with observations on both of the variables under consideration. And what this means is that the correlation between, say, variables x and y may be based on 495 cases, because only those 495 had valid observations on both X and Y, while the correlation between S and T, for example, would be based on 493 observations, because only 493 cases had valid observations on S and T. So, in other words, this correlation matrix that we see here, each of the correlations within it may be based on different numbers of valid observations. And there are, of course, other ways to go about doing this. So instead, you could look at only the cases that have valid observations across all 7 variables. So then we have one valid sample size of, say, 490, and then we could use only those 490 cases to compute this correlation matrix. Something else of note are the ones that run down the diagonal, which makes sense because each variable is perfectly correlated with itself. And then on the triangles that are above and below the diagonal, these are mirror images of one another because the correlation of X with Y is the same as the correlation of Y with X. Okay, so let's look at one final example here. So here we have the scatter plot of the interest in internet, computers, and technology with their use at school. So how would you describe the relationship between these two variables, and what would you expect the Pearson correlation to be between them? Again, feel free to pause this and think about it, and then I'll point out what I would expect the relationship to be and maybe a rough guess at the correlation, and then we'll see what the correlation actually is. Okay, so looking at this scatter plot, something that quickly stands out is that little point up in the right-hand corner. So we do also have potentially an outlier, maybe univariate on the use at school that we might want to take a look at. Then looking at the main body of points, there doesn't seem to be a particularly strong relationship between these two variables. We do see a general scattering of points, and if we were to imagine sort of a regression line on there, it would be pretty flat, maybe a little bit of a downward slope, but not much. So I would expect this to be small and maybe negative, so let's guess negative 0.0 something, but let's actually see what the value is. So the Pearson correlation between these two variables is negative 0.023, so it is negative. It is very small though, it's close to 0. So overall, there doesn't seem to be much of a linear relationship between interest in internet, computers, and technology and their use at school. Okay. Then if you need any help with your research methods, whether that be with regard to descriptives or elsewise, feel free to reach out to us via our email. It's drhelp@indiana.edu. We do have consultations available both in person and virtually, or visit our website at education.indiana.edu/researchhelp.